So let's. Okay. So yesterday I started writing this. So far we know 2A string theory, 2B string theory, then type 1 and hydraulic. That's what we're doing. So these have n equal to 1, and these two have n equal to 2, but different n. One is chiral. And then also, so this, let's say the supergravity of these theories are already known in the late 70s, early 80s. By late 70s, people already knew the type 2A supergravity in 10 dimension, type 2B supergravity, and the n equal to 1 supergravity. So these things they already knew, and they also knew that type 2A supergravity can be obtained starting from 11 dimension, from d equal to 11, n equal to 1 supergravity. So in other words, if you start from d equal to 11, n equal to 1 in d equal to 11, and do a dimensional reduction on a circle of, just do a dimensional reduction to 10 dimensions. So say compactify on a S1 of radius r, and take the limit r goes to 0, then you get a 10-dimensional theory, a d equal to 10 theory, and that is type 2A supergravity, not string theory, supergravity. So this they already knew. So, of course, before this duality discussion started, before saying that until 80s or early 90s, people didn't think, most of the people didn't think there was actually any more relation between these two than just the fact that 2A supergravity, which is just the massless sector of 2A superstring, that can be obtained from d equal to 11 by dimensional reduction. Okay? But not more than that. But so no one really suspected there was a deeper relation between the two until this mid-90s, when the S duality started coming. So what I will discuss first is so I'm going to discuss this relation, because now what we think is that the strong coupling limit of type 2A theory is the 11-dimensional supergravity. Okay? This is the from the mid-90s we learned that if you take the string coupling constant, which is a dilaton of the type 2A, if you take the coupling constant to infinity or very large, then in that limit, the physics is basically described by 11-dimensional supergravity. Okay? So that's the first thing I'll talk about. So in some sense, d equal to 11 supergravity is the strong coupling limit of type 2A. That's one. So S dual of weakly coupled type 2A. S dual means the coupling constant goes to 1 over coupling constant. S duality is that. In type 2B, it was also known that at the level of type 2B supergravity, that if you look at the equations of motion of the type 2B supergravity equations of motion, then that had an SL2R symmetry. So what was known was that if you take 2B supergravity, only supergravity, not string theory, supergravity, then, and then look at the equations of motion, classical equations, then these equations of motion had an SL2R symmetry. Now, when we go to the string theory level, it will turn out that this SL2R, certainly SL2R cannot be true at the full string theory level, because that's only supergravity, only the massless states. Right? So for sure, this SL2R will not be valid in the full type 2B superstring. But so it should be if at all something is possible, it should be some discrete subgroup of SL2R, not the continuous SL2R group, some discrete subgroup. And what the conjecture is that type 2B is SL2 has SL2Z symmetry, SL2Z duality symmetry. This SL2Z also includes a transformation which takes the coupling constant to 1 over coupling constant. So that means the type 2B is S dual to itself. So the strong coupling limit of the type 2B theory is again another type 2B theory with weakly coupled, which is weakly coupled. So that's what. So it's self-dual. And then finally, if you look at n equal to 1 theory, once again, you remember in type 1 theory, there is the gauge group is SO32. So it turns out that type 1 theory and heterotic theory are S-dual. In other words, strongly coupled heterotic theory is a type 1 theory and vice versa. So this is what we know. And already we have seen that these two are related by T-duality. And as well as these two are related by T-duality. These parts we already have seen. T-duality part we have already seen. And T-duality is not a conjecture. It is, I mean, you can, it is valid order by order in coupling constant. Okay. So that is already the string perturbation theory. You can see that that is there, T-duality theory. The rest of the stuff is, of course, conjecture. Because when you talk about strongly coupled theory, you don't know, you cannot solve it exactly to check. It's a conjecture, but there are many evidences that for this conjecture. It's not a complete proof, but nevertheless, there are many strong evidences which point to the that this probably is good, it is correct. Okay, so let me start from this 2a d equal to 11. So I start from d. So let's look at the d equal to 11 subgraph. This is very simple field content. This is supergravity in 11th dimension. So this is n equal to 1. N equal to 1 supergravity. This is a very simple field content. It has just two fields, the metric and a three-form antisymmetric field. This indices m, n, etc. will be running over the 11th dimension. So m, n, etc. from 0 up to n. So 11th dimension. So it is just very simple field content. And what is the action?
You need two bosonic.
Sorry?
Two bosonic fields. Two bosonic.
Ah, yeah, two bosonic. Plus, of course, the fermionic partners. I mean, I'm always writing only the bosonic parts. Plus the fermionic partners. And the action, again, I'm going to write only the bosonic part of the action. It's simply D11x, and then you have R, plus, again, I'm not going to worry about the coefficients and so on, just schematically. So it is F4 squared, right? F4 is the field strength of this freeform. F4 is this DC.
Sorry. How do you get that field?
Well, that is you have to look at the super. I mean, you can show that this super n equal to 1 supergravity closes in this place. Okay, you can write down supergravity transfer.
Yes, right.
Sorry.
On share.
Yeah, on share. So you can, yeah. This is a long. I mean, in the late 70s, there was a huge amount of work done on supergravity by various groups. So this was the basic field. Plus the fermionic. There is also a Chern-Simons term, which, okay, I will not include. So plus some Chern-Simons term, plus the fermionic terms. Because in fact, you see that for most of these discussions, really details of the actions will not be important. Because most of the arguments will be scaling arguments. So it will not be important details. Coefficients are not important. Square root of g, of course. Okay. So this is the 11th dimension supergravity action. And type 2 we already know, type 2a. This action is d10x, square root of g. And then you have r e to the power of minus 2p. And then you have R plus dp square plus h square plus f4 square plus f2 square. These are the Ramond fields, right? The Ramond fields in the type 2A are one form, C1 and C3. These are the Ramond fields in type 2A. In type 2A, it's odd form potentials. In type 2B, is even form potentials. So these are the plus again the Fermat. Plus the Chern-Simons is the Chern-Simons plus Fermat. Okay. So we have to, of course, go from 11 dimension to 10 dimension, right, to relate the two things. So I start from this theory, go compactify on a circle, and go to 10 dimensions. This is that. So we start from 11 dimension and equal to 11, compactify on a circle of radius r, and come to B. So I can write down the metric, the 11-dimensional metric, d square, what shall I call 11-dimensional metric, as some. So okay, let me do the following. So let's again look at the metric GMN. When I do the reduction, again it decomposes in terms of the G mu nu, G mu m, G mu 10, and G10. Right? I mean, so I just started with 11 dimension. These indices are 11 dimensional indices. So mu nu are the directions along the 10 dimensions, and then there's of course the 10th direction, which is a circle. So x10 is identified with x10 plus 2 pi. So that's the. So I just decompose this in terms of Lorentz under the representation for the Lorentz group acting on the in 10 dimension space. So this is the metric. This is the vector field. This is just one gauge field, and this is the scalar. Okay. Now I will write this. Okay. So I can parameterize this one scalar by something called phi. So I will parameterize this by some scalar field phi. G1010 is a scalar field. I will just define it. I will represent it in terms of scalar field phi, and I will write it like this. So say e to the power of some number times phi times the dx mu, dx mu. So maybe I should just write it like this. Some okay, g mu dx mu dx mu. So that's that. And then I will write e to the beta phi times dx10 plus a mu dx mu square. So I'm writing in a particular way. There is a reason for writing like this, but you see that it has everything, right? So e to the alpha phi times g mu nu is the 11-dimensional g mu nu. So in other words, g mu nu is e to the alpha phi times g mu nu. And g mu 10 is just a cross term, dx10 times dx mu, right? When you take the square, there will be a cross term. So that would be, no, sorry, there's one more term here, plus e to the beta phi here times a mu, right? Because there will be also a term which will come from square of this, which will enter here. Right? So it will be a nu times e to the beta phi. G nu 10 will be simply e to the beta phi times a nu, and G 10 is e to the beta. So I have just parameterized these three quantities in terms of this quantity G mu nu, the phi which enters the G 10 and a nu which defines the G 10. So it's just a convenient parameterization. Then what I'm trying to do is I'm going to identify. So this will turn out to be the type 2A metric. In type 2A there is a string frame metric. So I'm thinking of this as a type 2A string metric, G mu. And I've taken out some factor into that. These numbers have to be determined. Alpha and beta are some numbers. We have to determine that so that, I mean, this, once you plug in here, it should reproduce that action, right? So that will determine what is alpha and beta. The fact that it is guaranteed that you can find a solution for alpha and beta is because there is a unique, I mean, at this n equal to 10, n equal to 2 at 2A supergravity, there is a unique action. Okay? Up to field redefinitions. You can redefine your field, but the action is unique up to field redefinition. So you are guaranteed that you will find some alpha and beta such that this is true. Right? So what I want to do is that I want to substitute these maps, substitute these fields here, okay? And then I want to get back the type 2A. Is the logic clear?
What happens with the Ramon and the other field? I mean, with the C?
Yeah. I mean, I'm coming back. So at the moment, I'm just writing the 11-dimensional metric.
So you want to reproduce the first line?
No, actually, yeah, everything. All of this. So this was so far the metric. Now what happens to the three-form potential? C3, M, and P. Once again, I can decompose in terms of the D equal to 10 Lorentz group. So this will give you C3 mu nu rho. And then C3 mu nu 10. Right? So now you see this is a second rank antisymmetric tensor as far as the 10 dimension is concerned, right? Under the it is a second rank tensor in 10 dimension. And you see that here the field content. So what are the field contents here? So of course there is the metric, the 10-dimensional metric, which is what I'm calling this metric. Then you have the phi, one scalar field, and that is this scalar field phi. And then you have the H. H was a field strength of a 2 form, right? And here we have the 2 form. Then we have a 3 form Ramon. There is a 3 form here, 3 form potential. And finally, there is a field strength, second 2 form field strength, so it is a 1 form potential. That 1 form potential will be this A mu. So all the field content is there, the bosonic field content, right? You see that. But now what we want to do is to reproduce that action. So let us see how we do this. And I mean, we still have to determine this alpha and beta. These numbers are determined, so that this action is mapped to that action.
And the fermions?
The fermion will automatically work. That's not a problem. Because once you have, I mean, the reason why I'm doing this, you see, I'm guaranteed by just the uniqueness of the action, uniqueness of the n equal to 2 theory in 10 dimension, n equal to 2 non-chiral theory in 10 dimension. I'm guaranteed that this action will reduce to that action. But the only reason why I'm going through this exercise is to understand the field, particularly the bosonic fields. What do they mean in the 11 dimension? Okay? What is the geometric meaning of those fields? In particular, I'm interested in finding out what is this dilaton. What is this dilaton in the 11 dimension? The dilaton in 11 dimensional theory, as you can see from here, is related to the G1010. And G1010 is nothing else but R square. Right? G1010 is R square. So the radius of compactification of the circle is related to the dilaton, and therefore the string coupling constant. But now what I want to do is to find out the precise relation between the string coupling constant and the radius. That's the purpose of this. Okay, so let's see. So now let's try to see how the thing scales. How does the metric scale? So first of all, let's look at the R. So this R is of the G mu nu. This R is of the G mu nu, the 10-dimensional metric. Right? This as far as type 2A is concerned, this curvature is computed from this 10-dimensional metric. So it is that. And now, how is it going to scale? So what is this scaling here? G mu nu is e to the alpha phi G mu nu. So in 11-dimensional theory, I'm computing, so this is a 10-dimensional, this is in 2A theory. Right? In 11-dimensional theory, what I'm computing, this curvature R is a curvature of 11-dimensional metric. Okay? It's a curvature of 11-dimensional metric. So, so in particular, so there will be terms, for example, R mu. So I want to compute this curvature in this metric, in this way of parameterizing it. Okay. So look at this part, the 10-dimensional part. So it's basically, we're looking at terms like R mu nu, or just look at R, of e to the power of alpha phi G mu nu. I want to look at this term. And again, details are not important. Really, the important part is the scaling, how the scaling is working. Because finally, I know the action is going to reproduce the same action as a type 2A, up to field definition. So for me, only important thing is to see how this scales, how this object scales. Now, let's look at this. How does curvature scale? How you construct the curvature scale? Well, first of all, maybe I can do it here. To construct this from a given metric, you first construct the Christoffel connection, right? How does the Christoffel connection look like? Suppose it's something like this here, the lambda, mu nu lambda. It's defined, again, numbers I'm not going to worry about, signs I'm not going to worry about, because those are not important. But the main point is that it's something like this, G mu nu, and then two other terms. But they are all of the type, there's a derivative acting on the metric, right? And there's an inverse metric. Right? Now suppose I scale the metric G by some e to the alpha phi times G, which is what is happening here, right? You have e to the alpha phi times G. So when I scale like that, there will be, I mean, of course, when I G mu nu is scaled like this, then G lambda sigma, because this is the inverse of that, will scale the opposite way, right? This is going to scale like e to the minus alpha phi G lambda sigma. So you see that here, this picks up e to the minus alpha phi, that picks up e to the alpha phi, so it doesn't scale, right? So this remains in the end. What about the Riemann tensor, R mu nu lambda sigma? This will be obtained from the Christoffel connection. So d mu gamma nu lambda sigma, antisymmetrized between mu nu, and then there's a term which is gamma gamma.
Sorry. Does it have a derivative term?
Derivative, but it doesn't matter. That's what I was telling you, that it's not important, because the derivative terms are going to give me, derivatives are going to act on the phi, right? But after all, there is a kinetic term d phi. So all those terms are going to, or the kinetic term of d phi will come from that part, when the derivative hits the phi. Yeah, true. I mean, that's essential actually. Otherwise, you wouldn't get this, the kinetic term for the phi. But again, as I said, all of that is guaranteed to work. For me, the important point is to find out what is the value of alpha and beta.
So could you repeat everything? Like, why is this guaranteed
Because there's a unique supergravity theory.
in 10 dimensions?
In n equal to 2 supergravity theory in 10 dimensions. Yeah. Up to field definition, by you making some appropriate field definition, you can go from one to another.
So, how can we know that supersymmetry is preserved?
When you compactly when a circle supersymmetry is preserved, right?
Every time.
Yeah. This is flat space. Also, there's something, okay, since you asked me this question, I remember. I wanted to explain to you why I'm writing like this. Okay, let me just complete this argument and I'll come back to that. That's an important point, why I'm writing like this. Okay, so you have something like this. This maybe the two gammas. Now, how is it going to scale again? We are interested in how it's going to scale. We already said gamma doesn't scale. Okay, so this is also not going to scale because there's no more additional inverse metric or anything like that. This is also not going to scale. Of course, there will be derivative terms on the phi. All that will be there, but the scaling will not be. Will not scale. Now, what about the let's say the Ricci tensor? Well, that's nothing else but just the contraction of the Riemann tensor, mu, nu, lambda, nu. Nothing. We are not doing anything. We are just setting sigma equal to nu, right? So if this doesn't scale, this also doesn't scale. So this also doesn't scale. But finally, when you consider the curvature scalar, that involves an inverse metric. Okay, mu lambda. So curvature scalar involves an inverse metric. So that means under this scaling, under that scaling there, curvature scalar goes to e to the minus alpha phi times r. Right? Because g goes like e to the minus alpha. G inverse. Right? This is the upper index. This is the inverse of the index. So the conclusion is that this, when you construct the Riemann Ricci scalar from e to the alpha phi times g, you will find it is this curvature scalar would be e to the power of minus alpha phi times r evaluated on g. Plus, as I said, I mean, as the question pointed out, there are derivative terms in phi, square, whatever derivative terms are there, but those are just going to reproduce that. So I'm just focusing on distance. Okay, that's one thing. But also now I have to look at the square root of determinant of g. Square root of determinant of g is what? It is so you have this factor. So what is square root of determinant of g? So g, let me call it 11, g 11 dimensional metric. Well, you'll have, so if you look at the g mu nu part, so there will be a g mu nu part, square root of g mu nu. I was using little g mu nu, determinant of g mu nu. But this is a 10 by 10 matrix. Each of them is scaled by e to the alpha phi. So your determinant will have e to the 10 phi, but then you're taking the square root. So you'll get e to the 5 alpha. Yeah? So there will be e to the 5 alpha phi. That's coming from just the 10 dimensional part. And then from the last 11th dimension, you have got an e to the beta phi, right? But then you have a square root of that. So you get e to the power of beta by 2. So this is what the 11-dimensional determinant will be. Now let me come back. So okay, so before coming here, let me just finish this up. So altogether, we are seeing that this term, so the 11-dimensional R is giving the times square root of G11, square root of G11 times R11 is giving, first of all, this gives you a factor of e to the 5 alpha phi plus beta by 2 phi. That comes from the determinant factor. And then you have an e to the minus alpha phi coming from the scaling of the Ricci scalar. So minus alpha phi. Sorry? So somebody said something? Okay. So times R, times the R evaluated in G mu nu. Now just compare this term here. So that term, that whole combination, and times square root of G. Times square root of G. This G. So one equation you immediately get is 5 alpha phi plus beta by 2 phi, so minus alpha, so 4 alpha phi plus, unless I have made some mistake, I hope I have not made a mistake, should be equal to -2, right? Because this factor is equal to -2. So that gives you one condition on alpha. Now let's look at some other object. So, for example, we need one more equation because we have two unknowns, alpha and beta. I need to have two equations to get to this one. And then it's enough because then everything else has to match. So you can look at some very convenient term. For example, let's say f4 squared. F4 squared. Yeah, maybe you can just look at f4 squared. So here, this f4 squared directly descends to that f4 squared, right? You just have to restrict. I mean, this f4 has m and pq, fm and pq, fm and pq, right? Just restrict m and pq to mu nu lambda sigma. Then it just directly comes here, right? However, there's a metric here. So if I look at f mu nu lambda sigma, which is part of that, part of the full 11-dimensional, right? And then you have f, I don't know, mu prime, lambda prime, sigma prime. Then there is a metric. This is an 11-dimensional metric, but then I can write it as, let me just write this 11-dimensional metric, mu prime, etc. G, sigma, right? To get the scalar. F squared means that. You have to contract. So what you find here, each of these guys, these objects become G, mu prime, etc. G, sigma prime. But in that process, you become e to the -4 alpha phi, right? Because each of this metric, G's become e to the minus alpha phi. There are 4 such factors, so you get e to the -4. So this term picks up. So the root. So that means root G11, R11, not R11, F4 to the F4 square gives you, among other terms, there will be many other terms also, but in particular this term, which will be F4 square in the 10th dimension, okay, times e to the minus 4 alpha phi. Okay. And then we have the determinant factor, root G, which I just evaluated, yeah, which is plus 5 alpha phi. So this is giving e to the 5 alpha phi plus beta by 2 phi times square root of G. And now you see the overall factor of the alpha. So this is nothing else but e to the power of alpha phi plus beta by 2 phi times square root of G. Square. Now compare that with the type 2A action. Here there is no dilaton factor. There is no dilaton factor because remember this comes from Ramon in type 2A. So that means alpha plus beta by 2 is 0. So the second equation we were looking for is alpha plus beta by 2 is 0. So now you can plug that back here. So beta by 2 is minus alpha. So this simply becomes 3 alpha equal to minus 2. So that means alpha is minus 2/3. Is that correct? Yeah, minus 2/3. And then beta is minus 2 alpha. So beta is 4/3. This one. Now let's just check whether this is true. I said that this is enough. I mean, we can just once you have this, then this action is automatically going to map to that action. But let us just to double check. But before doing that, let me come back here. I want to erase this part. But before erasing, let me just come to this why I'm writing this. Because in writing, I mean, you could have written GMU 10 in any way. You could have just written it as, after all, this just gives you a cross term, right? The main part is it gives you a cross term. But I could have written it just as GMU 10. Dx mu dx 10, right? But this way of writing it makes a gauge transformation, gauge invariance, or gauge transformation of mu very explicit. Okay? And why is that so? Let's try that. Let's look at how that works. You see, this is going to be a U1 gauge field in 10 dimensions. This is going to be a U1 gauge field. So that means I should have some gauge invariance which takes a mu to a mu plus d mu of lambda. Lambda is any function of x's, right? Lambda is any functions of x's. So this should be the gauge invariance, right? And what I'm claiming is that this is this way of writing it, it makes it very nice. So how you do that? So let's make that transformation. We are looking at dx10 plus a mu dx mu. Well, this will go over to dx10 plus a mu dx mu plus d mu lambda dx mu. Right? So this will go over there after the gauge transformation. But d mu lambda dx mu, this guy is nothing else but d lambda. Right? Lambda depends on only x mu's. So that becomes that. But then I can reabsorb it. I can write this as dx10 plus lambda plus a mu dx mu. Right? Now x10 plus lambda I can just call some x10 prime. That is just a reparameterization, diffeomorphism. Right? So what we are seeing is that the gauge transformation, U1 gauge invariance of U1 gauge transformation is equivalent to a diffeomorphism in 11 dimension. And since the 11-dimensional theory was diffeomorphism invariant, therefore whatever you will get in 10 dimension will automatically have U1 invariance, U1 gauge invariance. So that's advantage of that. By the way, this is a very general phenomenon. Here it was just U1. Suppose that you had not a compactifier in a circle, but you had a compactifier in a two-sphere. Just imagine. Suppose a round two-sphere compactified. On the round two-sphere, you have 3 killing vectors. Okay? So you can expand this part in terms of the 3 killing vectors. And then the resulting gauge group you will find will be the SU2 gauge group. This way of writing. Okay, it becomes slightly more complicated than this, but I mean, something of this kind. So we are guaranteed, this way of doing this, we are guaranteed that whatever action we will get should be gauge invariant, right? When you plug this in here, that means it will be expressible in terms of F mu nu, right? Because the gauge invariant quantity of A mu is simply F mu field strength. So you will get terms of this type, F squared, F2 squared, right? Not some crazy thing which is not gauge invariant. It's going to be always expressible in terms of F. But so let's look at one more term, for example, what term? Okay, let's look at this term, for example. Just to make sure that, just to convince you that this solution we have found, alpha equal to minus 2/3 and beta equal to 4/3, will also give me the right factor for x squared. Okay. What is x squared? H squared, H was simply, remember what was H? H is this 2 form. This 2 form. This is going to be H mu nu. I mean, the field strength of this will be the H mu nu. Okay? H mu nu is the field strength of the Lebesgue B field. Lebesgue B field is a 2 form. So what I'm saying is that this guy should be mapped to the Lebesgue B field. NSNS B field. Right? So when I do this, all that is going to change here is instead of the one of the index will be 10, right? Because so this is d mu of c mu lambda 10, right? Right? I mean this will be the F3. F3 will be from the point of view of 11 dimension. In 11 dimension you only had F4. So if it is going to give you an F3 in 10 dimension, the 4th index must be 10. That must be the 10th iteration, right? So you have this here, and here also you have 10. So one of these, so there will be 3 of such factors, and one of them will be G1010. Right? That is what you will get in the F3 square. This will be F3 square. So what will be the factor now here? So this will be, this is what I call H3 square, H square, call this. With this factor will be e to the power of minus 3 alpha phi, because only there are 3 such factors here. And then there is one G1010, and G1010 was e to the beta phi, right? G1010 was simply dx, coefficient of dx10 squared, which is e to the beta phi. So inverse will be e to the minus beta phi. So this is minus beta. That is the factor you get. And now you have to multiply by the factor which comes from the root G11. So what we find is that this F4, this F3 square is equal to this coming to root G. So that part is the same. Only difference is here. It's now e to the minus 3 alpha phi minus beta. Now if you plug this all, let's see. So this is 5 alpha minus 2 alpha phi, which is 2 alpha phi. Minus 3 alpha is 2 alpha phi. And then you have beta by 2 minus beta by 2. So minus beta by 2 phi. And now plug that in here. So you get here 2 alpha, so minus 4/3. And minus beta by 2, so minus 2/3 phi, which is equal to minus 2. So indeed, you find this e to the minus 2. So you can repeat this. So maybe I should leave this as an exercise to show that f square comes with no factor, no exponential phi factor. Where f square is coming from, it's just f2 square is simply the field strength of a mu. A field strength of a mu square. Okay? So you can do that. It's not so straightforward. You have to do something because that will come. This term is going to come from the curvature, this curvature term. Because this curvature term has many pieces. We are focused on just the r mu nu lambda sigma part. But you'll also have r mu 10. Some of the index can be 10. Right? From that, you will find f2 square. So it's a little more complicated, but you can try. You can try that. Also, d phi square that comes to e to the minus 2 phi. But anyway, the upshot of this is that all of this entire action is mapped to that action with alpha equal to minus 2. So in other words, we have our map here is alpha is equal to minus 2/3 and beta is equal to 4. This is the main point. All right. So what is the, let's now look at a bit more, just a bit more to see the structure here. Now, on the type 2A side, we have two Ramon-Ramon fields, right? You have a C1 and C3 on the type 2A side. Okay, so what kinds of D-branes you have? Since you have learned D-branes, let's just check if this makes sense when you apply it on the D-branes. So the D-brane is, so C1 will couple to D0 brane, right? Because the world volume is one dimension. C1 is one form. And C3 will couple to D2 brane. Right? So we have this D0 brane and D2 brane in type 2A. Of course, there will be magnetic dual of that also. But let's just focus on the electric part, electric D-branes. And apart from that, there will be also we have so let's see. We have the B2, the 2 form, the Navier-Stokes 2 form, that will couple to the fundamental string. This is a fundamental string. Yeah.
Sorry, maybe the question is not for you, but you can answer. Like I thought that there's no open strings in the type 2B or type 2A.
No, there isn't.
So you still can have the brains.
So good point. Actually, to tell you the truth, when Bolshinsky's paper first came out, I could not understand it, for the same reason that you're asking. I mean, true, you can go through the calculations all make sense, but conceptually I couldn't understand, precisely for the reason that how come, after all, this big brains is some solitonic object in a closed string theory, right? It will have some gravitational background or whatever, and I should be able to scatter gravitons, etc. Just a closed string. After all, string theory only has a closed string. So you should just be, you just put the background of the, whatever the classical solution of the D-brane is, put it in the sigma model action, and you should be able to study the closed string. Of course, there is a technical problem in that, immediate problem, that at least in the formulation we are using, which is called RNS formulation, Ramond-Neville-Schwartz formulation. We don't know how to couple Ramond-Ramond fields, right? And D brane is charged under Ramond-Ramond, so it sources the Ramond-Ramond. So in the background, there will be Ramond-Ramond fields turned on. But that's a technical difficulty, in the sense that maybe you don't use RNS formulation, maybe something else. But the fact that you have open string, that is a conceptual issue, right? How come in a closed string theory you have an open string? I will try to give an answer to you a little later when I discuss the SL2Z of type 2. At least this is the way I try to convince myself that maybe it's okay, right? But when I come to discuss that issue.
Sorry, what's the F1?
It's a fundamental string. Sorry. This is the fundamental string. Yeah. Because remember, the fundamental string is charged under B2. Remember the winding mode was charged under the B mu, or whatever the compiler. Yeah? So that's what the fundamental string is charged under. In fact, another way to say is that look at the Polyakov action. Polyakov action is D2 sigma. Focus on the Polyakov action which contains the P, right? So that is simply epsilon mu times epsilon, AB times dA x mu, dB x mu, d mu. But that's exactly the coupling. That's the coupling of any P form to the associated extended object. Right? So this is the fundamental. It's charged. Yeah. So now, we can compute. But what is the origin? Let's look at all these guys, and let's look at the origin in the 11-dimensional. What is in 11-dimensional theory? In 11-dimensional theory, we have a 3-form potential, right? F4 is the field strength of the 3-form potential. So 3-form potential will naturally, 3-form antisymmetric form will naturally couple to a 2-brane, right? So now in 11-dimensional theory, what objects you have just the only extended object is the M2 brane. So this couples to C3 of the 11-dimensional theory. This 11-dimensional theory. Because F4 is DC3, right? Perhaps I should have used some different notation for this, not to confuse with the C which appears in the type 2A. Yeah? I don't know, maybe I should just call it CM. So this is the 3 form which appears in the 11-dimensional. So there will be an object which will couple to that, and that will be some 2-brane, and I call it M2 brane because it's in 11-dimensional theory, not in 10-dimensional. But this M2 brane will have some extension, right? It will have M2 brane will be lying on in the time direction, the 0 direction, and it can be either in the space-time part, some new part. Okay? In other words, all the 3 directions in the world volume could be in the space-time, in the 10-dimensional part, or the two possibilities, or it can be 2 of the directions in the 10 dimension and the 3rd direction, 10th direction. Right? There are 2 possibilities because this will be in general M and P. Right? The 3 in 11 dimension, the 3 directions could be capital M, capital N, capital P. But then there can be 2 possibilities because now they are compact defined. Right? So either all the 3 indices are lying in the 10 dimension, or 2 indices are lying in 10 dimension and 1 in 10 dimension. One is wrapping on the circle. So this will be a wrapped M2 brane which is wrapped on the circle. And this will be transversal to the circle. So this will still be a 2 brane in 10 dimension. So this guy should be interpretable as that object. Right? And this guy from the 10-dimensional point of view is a string. Right? Its world volume is 2-dimensional. Viewed from an observer sitting in 10 dimension, this will be a string. Okay? And so this must be the fundamental string. What about the D0 brane? By the way, you can also do this for the magnetic version. So here there is this. The magnetic guys will be. No, okay. Let me not. I'll just leave that as an exercise. Right? I think I'm not getting time. Oh, it's 3:30. So what about the D0? D0 is charged under what form? Under this C1, right? D0 is charged under C1. But C1 is coming from where? We said C1 is coming from the A mu, right? This F2, which we say F2 is the field strength of C1, but this F2 is coming from the field strength of A mu. So A mu is identified with the C1. So this A mu is the C1 of the type 2A. So D0 brane is something which is charged under C1, but in 11 dimensional it is just charged under A mu from the 11 dimensional point of view. That means it's a Kaluza-Klein mode. You see, the Kaluza-Klein modes. You can make a Fourier series expansion on the circle, and the Fourier modes are precisely the charge under the A mu. So in other words, these guys are nothing else but the KK modes on the circle, on the circle, on this 10th direction circle. So this highly non-perturbative object in type 2A is a very simple object in 11-dimensional theory. It's just the very simple Kaluza-Klein modes. So can we now understand all of this from the, in some little bit more detail? So for example, let's see. We know that its tension of this guy and this guy must be 1 over G string, right? Which means it should be e to the minus phi. Can we understand that? Because from 11-dimensional theory, so let's look at the 11-dimensional theory. Oh, sorry, I'm too slow actually. So if I write down the membrane, the world volume theory of this object, so let's say of M3 brane. So let's look at the world volume of the M3. So M2. The world volume of the M2. So let's look at the two cases where all the three indices are in nu lambda. In that case, it will be dx mu, dx lambda times the square root of the 11-dimensional metric, right? I mean, the induced metric, I don't know, G induced metric, but G induced from the 11-dimensional metric. Okay. Now, since these are all in the space direction, 10-dimensional direction, so this factor will be simply e to the alpha phi times G mu nu. I mean, this induced metric will be obtained from this G mu nu. So there will be 3 factors of e to the alpha phi here. So therefore, this will be e to the 3 alpha by 2 times times the dx mu, dx lambda, evaluated in the type 2A metric. So this is the type 2A metric, but I just take out the scaling factor e to the 3 alpha by 2. But alpha was what? Alpha was minus 2/3. So you see that this is nothing else but e to the alpha phi. This is nothing else but e to the minus phi, which is 1 over G string. Okay. So what we are seeing is that this object, the tension of this object is 1 over G string. Now, to contrast it with that, let's look at the F1. F1 is the same as that object, except one of the directions is 10. Okay? So what I'm going to get here, in the case of F1 part, what I'm going to get is a similar structure, dx mu, and dx10. But dx10 I can integrate out, so that is okay. But now look at the determinant of this factor. There will be e to the power of now, not 3 alpha by 2, only 2 alpha by 2, because only there are 2 G mu nu factors, right? And one of the factors is G1010. But G1010 is plus beta phi, so plus beta by 2. Okay? This is what you get, the scaling. And so alpha plus beta by 2, but alpha plus beta by 2 is 0. So this goes like G string to the power of 0. And that's indeed what we expect for the fundamental string. Fundamental string is not a non-perturbative object, so it doesn't have a 1 over G string tension. And same thing you can do with the D0. D0 brane is simply Kaluza-Klein mode. Okay, and you can find again. Yeah, you can again reduce that. This goes like this. So I'll have to, unfortunately, I'll have to leave a lot of stuff for as exercise because this will take me a long time if I have to do everything. But all the concepts are there. This formula is the most important formula. Okay? And you use that, and you can get all these objects. You can get the dual of this is the magnetic dual is D4, which comes from M5 brane. The M5 brane is the dual of the M2 brane. So M2 brane, we have the magnetic dual of this guy is M5. Okay. This M5 can give you D4. If one of these directions, if the M5 is wrapped on the circle, then it will be a 4 brane in 10 dimension. That's a D4 brane. But what about the M5 brane, where all the 5 directions are in the 10 dimension? That will give me a 5 brane in 10 dimension, and that is the NS5 brane. NS5 brane has not been talked about here in this school so far, but that's nothing else but is a magnetic dual of F1. F1 is electrically charged under B2 form, and NS5 is just the magnetically charged. It has not been discussed in this lectures at all, but they are also there. The tension of this guy is 1 over G string, simply because this is a D brane. But tension of this guy is 1 over G string square. So I leave that as an exercise. So start from the M5 brane, and once you do not reduce on the circle, do not wrap on the circle, you should get this and show that this is the tension goes like 1 over G string square. This means e to the minus 2p. And the other case where M5 is wrapping on the circle, and show that the resulting thing will be a 4 brane in 10 dimension, and show that its tension goes like 1 over G string. So please try to do this exercises. It's not very difficult. It's not difficult. I think the difficult part is more this to get there, to show that this has no scaling, no e to the alpha. Okay, but all this is nothing big deal. I mean, this was guaranteed. All of these things are guaranteed to happen because of again the supersymmetry is so strong that first of all the fact that this can be mapped to that by some field definition, this was guaranteed. And all we try to do here is to find the field definition. Okay? What is the field definition which takes you from one action to another action? And secondly, all of these tensions, etc., that we are talking about here, they had to work out. Okay? They had to work out for a simple reason that these are all BPS states. Okay? The states that we're talking about, these D branes, NS5 brane, all of these are BPS states. And BPS states, there's a relation, tension is given by the charge, right? And once you have the same charges in both sides, tension is bound to be the same, right? In appropriate units. So that's what one is showing. The non-trivial test to say that these two theories are dual to each other is not in showing that the tensions are the same. The tension formula are the same for both sides after the field definition. But more importantly, what is the multiplicity of those states? You see, multiplicity of those states. Now take this case. This is very important, interesting case here. Here you have A mu, this is the C1, and the object which is charged under that is D0. Right? Now suppose I take n number of D0 planes, right? A collection of n D0 planes. So that will have n units of charge. Right? Now look here, we said the charge of this A mu is a Kaluza-Klein mode. Right? Yeah, when we expand, we can expand any field in terms of e to the power of in extend over r, right? This is the Fourier series expansion along the circle on the circle. So when extend goes to extend plus 2 pi r, nothing changes, right? So this n is a charge under that A mu. Okay? And we know that from the Kaluza-Klein point of view, for every field, any particular field, say G mu nu, take anything, any of the fields, when you do the Fourier expansion, for each n, there will be precisely one state, not more, right? So can you show that in here, in this, on this side? So what we, if the duality is true, then we should be able to show that for any collection, and a collection of n D0 branes, there is precisely one bound state. This is a very difficult thing to prove actually. Because these branes are, these are BPS, you can just move them anywhere. You can place two, say take n equal to 2. You have two D0 branes, right? These two D0 branes can be anywhere because there is no net force between them, right? That was precisely the point Clifford showed, that the total force was 0, right? So there's nothing, you can move anywhere, right? And you have to, these are called threshold bound states. Threshold bound states are the ones where the sum of the constituent, the energies of the constituents is equal to the energy of the bound state. Okay. Usually we are used to having much nicer situations, you know, where there's a truly abiding energy, right? Meaning that the sum of the constituent energies is greater than the energy of the bound state. So bound state is preferable energetically, right? And actually you have to put energy, to give energy to the bound state to split it out, right? But, so those are easier problems, but this is a threshold bound state problem. So what you need to do is to look at this system of 2 D0 branes or n D0 branes, look at the field theory which describes the interactions between the D0 branes, which means basically the effective action of the D branes. Okay? So if you have n branes, it's an SUN gauge theory, living on the D0 world volume. So it's a quantum mechanics problem, because D0 means only one time. So you have an SUN, supersymmetric SUN quantum mechanics problem. And there you have to compute the Witten index. Witten index basically gives you the information about the bound states. And that was a difficult problem. And I think almost immediately after these things were discovered, like within 2 years or so, there was a paper by Sethi, and perhaps there was someone else also, I'm not sure. Perhaps someone else also. This paper which came out, I'm not sure, 98 or something like that, 97, 98, where he does it for n equal to 2. That means you are looking at the SU2, SUSY, supersymmetric SU2 quantum mechanics, and there he computes the Witten index and shows that it actually is equal to 1, okay? Which is what is predicted from the, if the duality is correct, that's what you should get in D difference. It's a rigorous result. After that, I think there have been attempts, and probably by now, I've not been following the literature, but probably by now it has been extended to any n. I mean, there was already a paper by Shatashvili and so on, which extended to SUN, but there were some assumptions there to make. Okay? But I think by now, even those assumptions have been removed. So this is really a very strong result. If this is really has been proven, it's a very strong result. It's not the tension is not the important thing, that is guaranteed. The important point is what is the multiplicity of states. That has been said. Okay. Okay. Now let me come to the type 2B. So type 2B, and I will be much more, I will leave most of it as exercises because I really don't have time to go through this detailed calculation. These are trivial. I mean, you see, it's very straightforward, right? You just try to make some answers, you know, and then verify. But what I will do is I will just directly give you the answer in type 2B. So in type 2B, what is the field content? In type 2B, the field content, of course, there's a metric, G union. Then you have the dilaton and the B union. Those are there. In the Ramon sector, we have a C0, a 0 form. It's a scalar, so let me just call it chi. Give it a name chi, instead of writing C0 all the time. So there's some scalar, chi. And you have C2. Okay, then you write this also the same notation. There's a B2 and that is C2. And then you have a C4, where C4 is not completely, it's constrained C4. You must have seen it in Carvin's lectures. The C4 is constrained in the sense that its field strength, which is a 5 form. 5 is precisely half of 10, right? So in 10 dimension, you can talk about whether this 5 form is cellular or not. And in fact, this is constrained that the field strength is cellular or anticellular, depends on your convention. but it reduces the degree of freedom by half. So the F5 is, the corresponding F5 is the dual of this difference. This constraint. But anyway, this is not going to play much role. Most of the important role in the discussion will be these guys and these guys. Now, the action is d 10x square root of g times the e to the minus 2p times r plus square. I mean, there's a number here, 4, but I'm not, since I'm dropping all the numbers, I will not. There's x3 square plus the Ramond sector. Ramond sector is, there is nothing, there is no e to the minus 2 field factor, so there will be a d pi square. I mean, this is the dc0, field strength of c0 square plus dc2 square, or which is the same as, then we call it f3 square, and finally f2 square. Okay, this action is not, I mean, it's not, actually this action you cannot write. I mean, there's a problem with this. Type 2b, you cannot write an action because this F5 is self-dual. So in other words, you have to take into account the constraint. This F5 is not free. If you impose self-duality condition, this simply is 0. Okay. So you cannot write this term. However, you can at the moment just assume, forget the, I mean, you can forget that this F5 is self-dual, derive the equations of motion, and then after deriving the equations of motion, then put the constraint. Okay. So then if you understand this action in that sense, that at this stage I have to treat F5 as independent, okay, get the equations of motion, and then set this constraint. Then it's okay. Okay. Plus the fermionic terms, again, I don't worry about it. This,
Can you add the constraint to that action?
yeah, you can. I think you can do this. Yeah. Although I'm afraid experts are really upset when you write down. You know, the supergravity experts become very upset when you write down this action. They say, what are you doing? But I mean, really, if you derive the equations of motion from here, okay, you get some set of equations and then just put the constraint. Then everything's okay. All right. So now look at this here. Actually, there are some. Sorry, this is not complete story. There are. Maybe I should write this. There is one term which is pretty crucial. Let me put here F3 hat, and also F5 hat. What is F3 hat? F3 hat is equal to F3. F3 meaning DC2. This is a totally antisymmetric label. It's understood. It's totally antisymmetric. DC2. Plus there is a correction, which I'm not sure. Maybe minus chi or plus chi. Chi being the zero form times H2 times B2. D, which means H3. So this F3 is a combination, this F hat 3 is a combination of F3, this is the usual F3, and there's a times, and a combination of these. There are certain combination of these two, three forms. This is a little bit important. I mean, I'm being very sloppy, but this part is a little important. And similarly, F tilde F hat 5 is also a little more complicated. It is dC4 plus something, plus chi times something like, I don't know, B2 F3 minus B2 F3 minus C2. Okay, some such thing is there. There's some. Yeah.
How would I know that those terms are present there?
Oh, you can. First, there are two ways. One is the supergravity action. Okay. This is the only way you can complete to supergravity action, or directly compute the scattering amplitudes. I don't know if anyone, honestly, if anyone has done this calculation. Because everyone knows it has to work out. But I'm sure it will work out. There's no way it will not work out. I mean, it's guaranteed because supersymmetry is there. We know type 2B has that supersymmetry, so it has to. Okay, so now you see you can write this in a more convenient way. You have dp. So let's focus on first this part, these two parts. I can write this as d tau times d tau bar over imaginary part of tau square. And let me just define what is tau. Where tau is equal to chi plus or minus, I'm not sure, so let's say plus I e to the minus phi. Because you see, if you do this, so since it's a absolute value, d tau bar, so this guy, the numerator, is the same as d chi, right? The real part, and then the imaginary part, which will be plus d e to the minus phi, d e to the minus phi. Right? Which is, this part is the same as, this part is the same as e to the minus 2 phi d phi square. No, sorry, there is no e tau square. No, there is no e tau square. No, there is just. So this is indeed the term, you see. You have d chi square, which has no factor e to the minus 2 phi. And d phi square is coming with e to the minus 2 phi, which is constant. So this is a very suggestive way of writing it. So let me write it somewhere else here. These two terms, so I write it in a way. What is e to the minus 2 phi? It is e to the minus phi is imaginary part of tau. So e to the minus 2 phi is in tau square, imaginary part of tau. But let me just leave it as it is. So d 10x will g e to the minus 2 phi times r. Okay, that is one thing. And then these two terms I have put together as d tau bar. Right? By this notation, of course, you know what I mean. Mu, nu, j, mu, nu. Right? Not just writing shorthand. Shorthand notation. Okay. Furthermore, I can combine this and that into a nice form, which is so. Yeah. So let's look at this part here. So I can write this part as F3, F3 minus, if this sign is, I'm not 100% sure about this sign, but okay, if it is plus, if this is minus, it's minus, if this is plus, it's plus. But okay, so times tau H3 squared, times the complex quantity. Right? Because the real part of tau is chi, so it becomes F3 minus chi H3 whole square. That's the real part square. And imaginary part square is simply e to the minus phi H3 whole square, which gives you e to the minus 2 phi H3 square. So that part can be written like that. So there's no e to the minus 2 phi in this fact, it's only there. And then there is this F5 hat square. This will not play any role. Now, and for some deliberate reason, I'm writing this as tau. This tau we used for the worldsheet torus. Remember the tau that we used? And that had an SL2Z symmetry. This tau, you can show, now I did this as an exercise, that if you change tau to tau prime, where tau prime is A tau plus B divided by C tau plus D. Okay. This was SL2Z transformation. And at the same time, you change the metric G mu nu goes to G mu nu prime, which is equal to C tau. No, maybe I should have done it differently. Okay, sorry. I should have done it. I mean, in this formulation, it's a little bit more complicated. So the trick here is first you go to the Einstein frame. You know what is Einstein frame? So you redefine your metric in such a way that this e to the minus 2 phi factor disappears. And I think, let's see in this language it becomes more messy. So, I think this is e to the phi by 2. So the G string, so I should put a string. The G string, this is a string metric. This is RGS metric. And so G string is e to the phi by 2. E to the phi by 2 times G Einstein. So you go through that, and then, okay, these powers will change. I'm sorry, I should have, these powers change a little bit. So then this guy disappears here, so this guy disappears. And here you get some power. Here you get some power here. Here you get opposite power. Okay. So there are some changes here. But after you go to the Einstein metric, then you will find that this action should be invariant under that. And this is the Einstein metric. Goes to Einstein metric. C tau plus D, Einstein metric. This thing. And at the same time, this is important, that if I write, so let's say C2 and B2, this goes to C2 prime, B2 prime, which is equal to A, B, C, D, C2. Where this A, B, C, D are the element of SL2Z. So A, B, C, D. So A, B, C, D, A, B, C, D are integers, and A, B minus B, C. For this, I should have given you, to check this, I should have given you I think, yeah. So once you go to the Einstein frame here is, this disappears. So this is just, you have to do this little exercise. So when you do the scaling and make the transformation on the string action, to be string action, to go to the Einstein frame. So of course, by definition, there will be no e to the minus 2 phi here once you go to the Einstein frame. Also not there. Here, H3, I think, yeah, it's e to the minus phi. What is this? H3 squared. E to the minus phi. And here it is plus phi. Okay. Plus phi. Right. And b chi squared, this comes to the e to the 2. So this is the structure. And then what you have to show is that this action is this here. And now because there is an extra e to the 2 phi, I have to take that e to the 2 phi out, which becomes this divided by m tau squared. Yeah, so this is called m tau squared. And what else? Here, this whole thing divided by m tau. Yeah. Okay. So please check that. So forget the F5 square. F5 square, actually, the F5 doesn't transform. F5 remains F5. This transformation, the SL2Z transformation, doesn't act on this F5. So this is not. The important point is to show that these three terms under the SL2Z, this SL2Z transformation it gives you back the same action. So that is the SL2Z invariance.
Narain, why is it?
Sorry?
Why must there be integers?
Why is it?
Integers.
Yeah. So good. At the moment, it's any SL2R, right? So this part is SL2R. But you have to see that, I mean, you see the SL2R is acting, this is also making the transformation on V2 and C2. Right? But these objects have charged states, right? V2 is a fundamental string, C2 has a D braid, I mean, C2 has the is a D string, right? This is a D string, this is a fundamental string. These are charged objects. So if you make SL2R, continuous SL2R transmission, and these charges are quantized. So because of this electric magnetic Dirac quantization condition. So they are quantized. So this must be a transformation in some lattice. This charge lattice. Charges are quantized, so they are lattice. So therefore, it cannot be a continuous subgroup, a continuous group of SL2R. It must be only some discrete subgroup, and that's the SL2Z. Now, you can see, okay, so please check that. But there is one very important thing here. There are two things I will do here. I think next time, not now, but I will do one thing. This suggests, I mean, if you can prove all this, then you'll be immediately wondering, what has this got to do with the worldsheet tau? Because worldsheet tau has the same property, right? This SL2Z transformation. Because this SL2Z transformation is a natural modular group of some underlying torus, right? But we don't see any torus, geometric torus, right? So how do you? So it would be nice to understand that geometrically, right? And the way to do this, if I get time tomorrow, which I hope I would like to do that, is the following. Let's start from N here. I mean, 11 dimensions. Compactify the circle, okay, which we did before, and we got 10-dimensional 2A, D equal to 10, 2A. Okay. That's what we did before, the previous first one. Now let's further compactify on a circle, S1. Okay. Then you get D equal to 9, type 2A. Now you do T duality. T duality, as we saw before, takes 2A to 2D, right? So you will get a 9-dimensional 2D theory. In this process, how many parameters are involved here? In the first step, I have just the radius R, right? The radius of this circle, when I go back to the first step. In the second step, I have another radius, R prime. Okay, I call it R prime. It's another radius. But there is one more thing. Because type 2A has a one form, this A mu, or C1, remember? So I can turn on the Wilson line of that U1 field. Okay? So I can also have A9, or C1 9. C1, the 9, the 9th direction. This is the X9, this is X9. So the circle, around the circle direction, I can take a constant value of C1. Okay? This is what we discussed in the Wilson lines and hydraulic string compactification. Same thing. Wherever you have a gauge field, you can take a constant value in the Cartan-Sabatier, but this is U1 and E. So I have two real parameters here and one real parameter there. So there are three parameters. Okay. So you see that now, from this 9-dimensional point of view, okay, so since I have this chain, what I can do, I can look at, I mean, this I can obtain from 2D theory, a 10-dimensional 2D theory, D equal to 10. 2D theory by compactification on the circle S1 with some radius. Okay. So how many parameters are here in this theory? There is one radius here, let's call it R double prime. This radius, I mean, there will be some relations between them, but for the moment it's independent parameter, R double prime. And already type 2B theory in 10 dimension has two scalars. This one, phi and chi. Right? So you have this phi and chi. So this gives you another two. So here's phi and chi. So there are two parameters already here, two parameters, and here is one parameter. So there are three parameters here, which of course it should be there. I mean, since you can come from here and go there, or you can come from here, the number of parameters must be the same, right? So going from here, there is one parameter here. This parameter has the meaning of type 2A dilaton, right? And then you come down here, it has two parameters, total is 3. And this way here also 3 parameters. Okay. So now you can go back and we have all the maps, map from here to there. From here, of course, a direct dimensional compactification of the circle. Here I have this here. And then you can map these parameters back to those parameters. Or vice versa. You go take these parameters and map to that. Got it? And you'll find that, you see, in this language, what I've done, starting from 11 dimension, coming to 9 dimension, I have compactified in a geometric torus. Now there's really a geometrically a torus, right? The circle cross circle. So, and you remember what is this C19 lifted up there? C1 itself is, C19 is this nothing else but G10, 910. Okay, so we have G910, this is G1010, this is G1010, the circle radius, this is G99. So these three things are nothing else but the standard metric of a torus, right? The three parameters entering the torus, of which one combination is the overall volume, and the other combination can be written as a complex parameter, and that parameter is a tau. So here we have a torus compactification. This torus has three real parameters. Okay? These three real parameters splits into one real parameter, which is the overall volume of the torus. Okay? Which is, I mean, if you think of this metric, 2 by 2 metric, G1010, G910, G910, G99. This is a 2 by 2 matrix. The determinant of this, square root determinant of this is the volume of the torus. Okay? So that is one parameter. And then the remaining two parameters can be combined in a particular way, which is this complex structure tau. That is the geometric complex structure of this torus. And you can show by this map, going back here, that this tau that you construct from phi chi is nothing else but this tau. So this tau that I wrote down here, there is a tau. No, sorry, where is the tau? Yeah, this one, this tau. This is, let me call it type 2b tau. This tau is, when you map it, becomes a particular combination of these three parameters, which is the complex structure of this geometric torus, which satisfies SL2Z symmetry. Okay? So this is what this is saying. It's not a big deal. I mean, this type 2B SL2Z will be there, meaning that it's not an independent assumption. Once you assume this duality, that the type, this is a strong coupling limit of type 2A, okay, then this is automatic. This is proven, because this tau is nothing else but the complex structure of a geometric torus, and that is just a classical symmetry, not even in quantum theory, classical symmetry of this theory. Yeah. In this chain, the only assumption is here, because the T duality has been proved. There is no question about it. This is proven. But this part has not been proven. It's a conjecture. Right? We have many strong evidences. In particular, the last statement I made, where you have counting of states to match. That's a very strong evidence. Still, it's not a proof. No, it's not a complete proof. But nevertheless, if you accept that, then type 2B SL2Z is proven, or vice versa. If you accept that, then the other is true. That's one thing. Second thing, sorry, can I go for 5 minutes? Somebody asked me a question about, why are there open string? Right? Yeah, good. So let me just give you at least the way I try to understand. I mean, this won't be completely convincing, okay? But at least it gives us some intuition. Okay. In type 2B, there are two strings, right? There are two types of strings. One is an NS string, and other is a D string. Fundamental string and the D string. Because you have two forms. You have a B2, is a fundamental string which is charged under that, and you have a C2, which is the D string is charged under that. D1 ring, which is the D string, is one extension, spatial extension. And the other is a fundamental string. So in general, I can talk about a bound state I mean, I can take P fundamental strings and Q D1 strings, right? I mean, I can take a stack of Q D1 strings and a stack of P fundamental strings and put them together. The tension of the fundamental string is, of course, 1. I mean, I'm not worried about alpha primes and so on. I'm just looking at the G string, how this G string enters. It's G string to the power of 0, right? The fundamental string. So there's a G string to the 0. So P of them, it will be P times 1, right? These are all DPS states, so you just edit it, you just add them. So P times 1. Now you have Q D strings. The D strings have tension 1 over G string, right? So Q of them will be Q over G string. However, this is a fortunate case that when you form a bound state, this is a true bound state. The true bound state. And so the bound state, so there are something called PQ strings. PQ strings, which carry P units of B2 charge and Q units of C2 charge. And its tension has a simple formula. The tension of this guy, PQ, is equal to square root of P plus Q tau mod. Sorry, this is just the modulus. P plus Q tau. Modulus. So what is that? So writing it explicitly, this simply becomes P plus chi Q. Chi is the scalar field chi. Yeah, this chi. Tau was equal to chi plus chi to the minus. P plus chi Q square plus Q square. Q square e to the minus G string. Q square over G string square, because tau is e to the minus phi. The imaginary part of tau is e to the minus phi. So tau square is e to the minus 2 phi, which is 1 over G string square. And then I have to take the square root. This is what it is. P plus Q tau in the string units. Okay. So I have gone back to the string units. So this was written in the Einstein frame, but I have gone back to the string units. Now, this is the correct formula. There are various ways of proving it. One way is simply to look at the, but this you have not done. You have not done, I think. I don't think in supersymmetry course, Nathan described the central charge. At least I asked somebody and they said no. The central charge of the supersymmetry algebra. And even if you have described central charge, you need to specialize into this case to find. Because the BPS, after the forming the bound state, it will become a BPS state. Okay? And that BPS state, its tension is entirely governed by the BPS condition. It's just given by the charge, by the central charge formula. And you get it. There are other ways of doing it. In fact, there is a, I think, I'm not going to go through this, but there is a nice paper by Witten. I don't know, again, around that time, 96 or 97, or something like that, where he shows, he constructs a bound state between, say, one D string, and any number of strings, P number of fundamentals. And the idea is that you start from the you start from the D string effective world volume action. So D string, a single D string has, of course, the U1 gauge field. Okay. Just the U1 gauge field, and the world volume is simply two-dimensional, one time and one sigma. Okay. So you can turn on, give some flux. So basically just F01, right? F01, the world sheet direction is time, and the direction, spatial direction of V1. Okay? You can turn on the electric field, electric flux. And the quantity of the electric flux gives you the charge, the fundamental string. Okay? And then you just compute the Hamiltonian. And you find this formula. Okay, he did it for, I think he did it for only one D string, and also that too, with the chi equal to 0, chi set equal to 0. Okay? But you can generalize discussions. So, yeah, you can do this. So this formula is there. But what is that? This formula is very interesting. Okay? Of course, it is saying that it's a true bound state. But more importantly, with this formula, I would try to at least make some sense of Polchinski's this open string, appearance of open string. Because let's consider now the simple case, P equal to Q equal to 1. P equal to Q equal to 1. And let's set chi equal to 0. So expectation value of chi equal to 0. Okay? So then this formula tells me that the P11, and in the notation PQ, is simply equal to square root of 1 plus 1 over G squared, G string squared. Okay. On the other hand, if you look at the single, I mean P of 0, 1, meaning P equal to 0, Q equal to 1, that is 1 over G string. And P of 1, 0 is 1, order 1. This is a fundamental string, that's a D string. Okay. So now imagine I have a D string here, sitting here, and I shoot some closed string, some graviton or something I shoot. No? So what's going to happen? This closed string will come here. At some point, imagine the situation where this closed string is like this here, where a part of this closed string is lying on the brain. Now, this part will form a bound state, because that's energetically more favorable. It's going to form the bound state. And if you look at its energy, what is this energy? Is this segment of the string. It has this energy, this tension. So let's expand it in weak coupling. So in the weak coupling, this goes like 1 over G string. I can take it out. And then I have a square root of 1 plus G string squared, which is 1 over G string plus order G string. So plus, I don't know, 1/2 G string plus higher order. Yes? So in other words, but this was already the tension which was existing already at that point. So I want to see how much it has changed from what was existing already. What is changing is of the order G string, not of order 1. Right? So that means this part of the sigma modal action or whatever it is for the fundamental string simply doesn't contribute. Okay? And only this part, of course, is a fundamental string, has that tension here, this part. But this part or the fundamental string somehow kind of gets dissolved inside the D brain. Some kind of a flux tube is formed. Okay? So that part just disappears. So effectively you just get an open string here. So what this kind of an argument is saying, in the weak coupling limit, this open string description is good. It's pretty good. However, this also shows to you that as you increase the coupling constant, this open string picture of D brain is not going to be valid. Right? The D string is large, so you simply cannot ignore. The square root factor is there. Right? And you will, I mean, the open string description of D brain will break down if you increase the coupling constant. By the way, the same thing happens if you take NS5 brain. Sorry, just to complete NS5 brain. NS5 brain has not been discussed here. Its tension goes like 1 over G string squared. You can ask the question, do I also have an open string description of this? So let's try to find out, just like here, you can consider a fundamental, try to find a bound state of NS5 brain and fundamental string. So find a bound state of NS5 and fundamental string. So plus fundamental string. And you find that this bound state is a threshold bound state. Okay? Which means the energy of the bound state is the energy of this plus energy of that. So there is no way, it's not a square root formula. The tension of this is simply 1 over G squared from here, and from here is 1. So nothing happens. And indeed, there is no open string description for NS5 brain. You know, this is why NS5 brain is much less understood. We don't have a conformal field theory way of understanding NS5 brain. And that's the reason why it has not been studied much. Whereas D brain had a very nice picture. Yeah, so I think I will just.
Is there any quick question?
Yeah, I mean, you can come back to the 11-dimensional supervalue. Yeah, that.
That's why they have such a structure.
Well, I mean, we don't know. I mean, type 2A, we have this infinite power spectrum, right? In 11 dimension, we don't have any strictly or anything like that. We only have the massless fields, supergravity. So, now what are its excitations? We don't, I mean, there's not much one can say.
What is that?
That is 11, there is some M theory, some 11-dimensional theory, whose massless spectrum is this, that there exists some M theory. We don't know what that M theory is. This is what Clifford was saying, we don't know what it is, right? Which is whose compactification to wind up on a circle, on a small circle, very small circle, gives you a time. A small circle because the radius of the circle is related to the string coupling constant. So if the radius is small, type 2 string coupling constant is small, so equilibrium description is small. So that is what. Of course, massless spectrum will match. And what I described here is at least some of the DPS states also agree. This Kaluza-Klein mode, because there we know what the Kaluza-Klein modes are, right? And then the D0 bound states. This was a problem. And that I think has been solved and shown that they agree. The multiplicity. Yeah.
Okay, please. Thank you again.